All right, so homework assignment was 1 point what? And 1 point what? What? 1.19. So this one, list set?
Yep.
Returns a list like LST, except that the nth element using zero-based indexing is X. Okay, so we're taking in a list, the bucket we're going to replace, and what we're replacing it with, right? So we need our pattern that will allow us to do something so many times. We're going to be building up a result list, correct? So we're going to keep consing stuff on that we find until we finally get up to the location that we want. Then, instead of consing on the thing that we wanted, we're going to cons on our replacement thing, right? And then, I think, didn't I give you a hint for this one?
You said use append.
Then we're going to append on the rest of the list.
Actually,
That will keep us from having to keep going through multiple times and kind of remembering, did I already skip where I was? Wasn't that a good hint?
oh,
In retrospect. Otherwise, you would have, I mean, you could have solved it otherwise, but otherwise you would have had to tackle that problem of, I've already replaced bucket 2, so I'm going to keep doing the rest of it. No, and we can do that. It's not going to be a big deal. But here, we'll get rid of this old stuff here. So we're going to define, what was it called? ListRef? List set. LSTNX. List set to be a lambda that takes in an LST, and an X. An N and an X. So this is the list. This is the bucket we're replacing. This is what we're replacing it with. Right? All right. So we can go ahead and we'll just ask our standard. Well, we actually have a couple of different things we can do here. We can say if we're done with our list, do our final piece of the cons. So let's kind of solve this maybe the way without append first. You want to do it that way? All right. So we'll say if null LST. If I'm out of stuff, go ahead and boil down to the empty list. That'll be the final part of our cons. All right. Otherwise, I need to find out if what I'm looking at is the correct bucket. All right. So if I wanted bucket 2, let's say, based on zero indexing, the first time, so bucket 2 would be the third bucket, right? So if I'm looking at a 2, is that it? No. If I'm looking at a 1, is that it? If I'm looking at a 0, is that it? I'm going to keep counting that guy down. So if equal n 0. So if I'm looking at 0 as my count, I have arrived at my final destination, let's say, right? If that's true, then what am I doing? I'm going to cons my replacement onto list set of the cooter of list. Let me kick this down the line here. Passing it minus, I'll kick this down the line too, minus n1, and we'll just keep passing our replacement guy. It's not going to hurt anything. I could have changed it to whatever I wanted to at that point because this is the only time I'm ever going to do a replacement. Otherwise, I'm going to cons the car of list onto list set of cooter of list, also kicking it down minus n1 and x. So let me steal. This guy. Expects a pair. What did I give it?
Oh, you still the red bar. You have list spelled wrong there.
Oh. So is that the right output?
Yep.
So bucket 0, bucket 1, bucket 2 is replaced with this guy here. All right, so you see how my logic, what I'm doing here is, this is my pattern. And we only, well, the alternative way I'm going to do this with the append, I'm actually not going to use this pattern, but we are then assuming that there is a bucket n of our list. I'm not doing any error checking. For instance, if I say, give me bucket 2 of a 2 list, there is no bucket 2 of a 2 list, because the legal buckets of a 2 list are 0 and 1. So I won't be checking for errors on that guy. This guy would work for that, it just won't do a replacement. Because I have this pattern check of saying, hey, if I'm out of crap, I'm not going to be doing any cooters or cars. I'm just going to give you that nice little empty list. You finish your cons and move on with life. If you didn't replace anything, that's on you. Make sense?
Yeah.
All right. But if I still have stuff in my list, I'm going to ask the question. So what I'm doing here, let's say it's a new pattern. And it's really only a new pattern from the perspective of we're counting, but we're doing our counting while going backwards. So I'm saying, look, I'm going to start with n. This guy wanted to be bucket 2, let's say. And each time through, I'm just going to decrement n by 0. Bucket 2 is our third bucket. 2, 1, 0. Third bucket. Third thing, right? Okay, so if I am currently looking at a 0, that means I have counted down enough times that I am now at the correct bucket. If I'm at the correct bucket, what do? I'm going to call list set on the rest of my list on a number that's one smaller than before. I still need to do my count down because I want to make sure I'm not bucket 0 again next time. So I'll be at bucket -1, bucket at -2, bucket -3, so on and so forth. We will never hit n equals 0 again. We hit it once, we did our switcheroo, and now we just keep going into the negatives. All right, so if I'm looking at 0, I'll cons my replacement onto whatever's returned by list set on the rest of my list, one number smaller. And I could have passed this guy literally whatever I wanted. LOL or something like that, because I know I'm never doing another replacement if n-1, if n is currently 0 and I'm going to subtract 1 from it here, I can throw whatever I want in there as my replacement because I know I'm never going to do another replacement. I only replace when n is equal to 0. And it's only equal to 0 in this case one time, because the only time it was 0, I made it a -1. Go ahead.
Isn't this like an infinite loop case? Because once you do an n-1 there, then it equals -1, which is still considered false. Which would, oh, yeah. Okay.
I mean, you're not wrong. If I didn't have that,
Yeah.
if I just had perpetual recursive calls, yeah, it's actually, it wouldn't be an infinite loop because we'd run out of memory first. The way stacks are implemented is in system memory, and the way recursion is implemented using stacks. And we're going to see that later this semester when we implement recursion into our own language. Which is funny because there's been some famous languages in the past that weren't smart enough to have recursion. Anybody know, this is computer science trivia, a famous former older computer programming language that does not support recursion. I think all of you have probably heard of it. I maybe have even given you this fact in some class.
Is that Fortran?
It is Fortran.
Okay, I think you did give us that fact.
Yeah, Fortran, very famous programming language, kind of one of our earlier languages that was actually taught, did not support recursion. But not the end of the world, because you can do anything anything you can do recursively, you can do with a stack and iterative. Stack and a loop. Still pull it off. So fine, it's not built in, but we can build our own. No problem. All right, so we'll just leave it at LOL. I don't want to confuse the Ann Arbor folks with my code-based jokes. That's when you know you've arrived as like a computer scientist, if you look at code and you get the joke in the code. Okay, so once you get to that, then you know you're ready to become a professional developer. All right, yeah, so I mean, understand the punchline is I can put whatever I want there. Literally whatever. Because I am never going to ever use this value again. I'm only swapping once. All right, so this is the only reason I'm even passing anything here is because list set takes 3 parameters. And if I'm going to call it recursively, I got to give something. All right, so this is one way we can do list set. Questions on this one? That was really a 2-star?
Yeah, I was.
Man, too easy.
You talk about stars way too much.
Yeah, it was
Yeah.
very easy.
Only Luke cried himself to sleep?
I was working on 1.20.
The 1.20 was harder?
That's what I thought.
Okay, well, we'll see in a second. Let me show you the, here, I'm going to show you the alternate way of doing this one. Well, I think it's an alternate way, at least in my head it seemed like it was. I don't exactly plan ahead. I just want to give you hints. It's just kind of hope for the best. List n, x, like that. And so what I'm going to avoid here doing is I'm going to say if, I'm not going to do that. In this case, the end of my recursion is controlled by this guy. Okay, and that's what Austin was asking about, right? He said, hey, if I just look at this stuff down here, that looks real fishy. Okay, because you're doing recursive calls every single time, bad things are bound to happen. Okay, at some point you need to, the plane's nosedive and you got to pull up at some point. So right here, this is where we finally get out of our recursive calls. I'm not going to do that in our second list set version here. I'm going to call this like list set append. Yeah, let's call it that. So instead, what I'm going to do is I'm just going to ask the question from below. I'm going to say if n is equal to 0. If I've already counted down, then what am I going to do? I'm going to cons my new thing here. Let's see. What I'm going to do is I'm going to append the list of that thing onto the cooter of LST. Actually, that's not going to be correct either. Yes, it is. Yes, it is. This is fine. All right, so I'll append the list of X. So this wraps X in a list. It's the same thing as saying cons X onto the empty list. Those mean the same things. This makes a list out of whatever X is. Whatever element X holds, even if it's the list AB, it'll make it the list containing the list AB. All right. Go ahead.
Couldn't you just use cons X in the cooter list instead of a pattern?
Cons X and the cooter of the list is going to give me, no you can't. because so you want me to do this. Cons X onto the cooter of list.
Without a pen.
If you do that, oh, we don't need to make a recursive call. We could do that. That will work. Yeah, this is effectively shorthand for what I was just doing. What I was doing here is instead of using cons, I was turning this into a list, and I was saying glue these two lists together. But the result of this guy will be, so actually let's just call this list set short. So this was consing X onto the cooter of our list. No recursive calls. This will boil down to a list with this guy on the front of the entire rest of our list. And then if I'm not at n equals 0, then what I'll do is I will cons the car of LST onto list set short of the cooter of LST minus N1 and X. Like that. Cooter expects one argument but found 3. Oh, sorry. The cooter of LST. That's the first parameter. List set short takes 3 parameters. This is the first one, this is the second one, that's the third one. There we go. And this right here is effectively syntactic sugar. Actually, no, sorry. This right here is effectively syntactic sugar for, is that comment?
Yes.
For this. Append list X and cooter LST. That guy. So this is a list. We'll make this guy a list. Append glues 2 lists together, effectively downing the list by taking the parentheses off of them, giving you a single list with all the contents of both. So when I gave you the hint of append, this is what I was intending, but this does actually accomplish the same thing. Probably better. It is better. Why wrap something in a list if the very next step is to not have it as a list? But like I said, one downside of this guy is it will break if I try to call it on a list that's too big. So if I say bucket 4 for this guy, it'll eventually scream at me. Whereas my normal list set, if I pass it bucket 4, it's cool with it. It just never did a swap. We never got to a bucket 4. Does that make sense? All right, so, you know, we can say that this guy looks a little bit, I don't know, more elegant or something, but it does lack, we can say error checking. The other one doesn't have error checking in it, just happens to not stumble upon the error because we kind of have our exit cases. Hey, I'm out of stuff to check. I don't care if we hit your bucket or not. We're done.
Can you just add the null check in the beginning? It's still work.
Well, yeah, but I'm not sure then if that's really much better than the the other one, other than you're just not making additional recursive recursive calls. So you certainly could do that, or you could do this as a. You could probably, if you did this as a cond, it might look cleaner. So we could say something like define list set good as lambda LST and X. Then we can have a cond where we say null LST boils down to the empty list equal and 0 boils down to the cons of X onto the coder of list, else will cons the car of list onto the list set good of the coder of list minus n1 and X. And I think that should handle all the cases, I guess. There's that. We change it back to a 2. That. I'm not sure that, really, I'm not sure any of those is like substantially life-changingly different than the other ones. Just a couple different approaches to the same problem. So really, we probably should call this like good-ish. Because it really isn't any substantially better. All right, but we got to practice with cons and stuff like that. All right, questions on that one? Next one is 1.2. Count occurrences takes an S and an S list, and we learned last time exactly what an S list is, right? Didn't we put it in our Ninja? Oh, I just showed you about grammars in here. So an S list was what? It was either a symbol. It was a list containing symbols or S lists. Is that correct?
Yes.
Okay. That's what an S list was, containing symbols or more S lists. So this guy takes in something we're searching for, as well as an S list, and he returns the number of occurrences of S in that S list. Okay. Hardest part of this one is spelling occurrences. Huh?
I spelled it like
Define count occurrences to be a lambda that takes in an S and an S list. And this guy is going to count the number of things in that S list. And we can go ahead and do this with a con because that's our current cool kid. So we'll say if null S list. So if we're out of stuff to check. Now, if we're summing things, we're counting the number of things we run into. I'm done looking at things. I need to end my recursive calls. I'm going to go ahead and boil down to 0. I'll tack a 0 on to my ongoing running total, and that's not going to break my total. Make sense? All right, so if I'm out of stuff to check, return a 0. Otherwise, if symbol car S list So if the first guy is a symbol and he's the symbol we're looking for, so and symbol. Oh, you want me to use and?
No, do it.
I tried using it.
Whoa.
Okay, and what is the EQ? S and car S list. If both those things are true, if the first thing is a symbol and it happens to be the symbol, then I'll return plus 1. Let's see, let me kick it down a line. I don't know how that's gonna format. Plus 1 and then count occurrences on S cooter S list. All right, we definitely need to kick this down. There we go, that'll. So I'm looking at a symbol in the front of the list, and it happens to be the symbol I want. Add 1 to whatever count occurrences returns for the rest. Else, the car of this guy must be a S list, right? It's not a symbol, must be an S list. And if it's an S list, what do? I'm going to add whatever count occurrences returns for the car of S list onto whatever count occurrences returns for the cooter of S list. Go ahead.
Well, couldn't you end up getting like a symbol in that else that just isn't equivalent to that to as?
Could. Yep. So as I currently have this written, I only ever look at symbols if it's equal to it. Well, I look at them anyways, but I only do something if it's equal to it. So this else right here, I'm making the assumption. So really the fix to this is this. The fix to this, the best fix to this is actually probably not to use an and. That's actually probably the best fix. And looks cool at first, but it actually does open us up to that problem. So if we're looking at a symbol, then we really want to ask another question. If that symbol happens to be equal to the value we're interested in, then what do we want to do? We want to do all that stuff. If it doesn't happen to be equal to that stuff, here, let's kick this down here. Ooh, it was way uglier than I expected it to be. So if it's a symbol, then if it's the symbol I care about, add 1 onto whatever count occurrences is. Otherwise, boil down to count occurrences S cooter S list. This handles all symbols now. If it's a symbol at all, ask the question, is it the guy we want? If yes, add 1 to count occurrences for the rest. Otherwise, just call count occurrences on the rest. Go ahead.
Wouldn't we want to use EQV because we're comparing values and not memory addresses?
EQ will work for symbols. You have single equal sign, you have EQ, you have EQV, and you have equal. You have 4. EQ will work for symbols, I believe.
Okay. The rundown I read just said that EQ worked mainly on pointers.
You might be right. I would say I don't have a great understanding of the definitive differences between them. I've always just referred to single equal sign as numbers, equal is bone structure. So I would say I'm not necessarily sure in between, but EQ does work for symbols. Okay. So let's test this guy. Hey. Count occurrences expects 2 arguments, and I only gave it 1. Oh, which guy was it screaming about? I got bat parentheses somewhere. Right here. Ah, gave it the car. Why did I give it the car of S-list? Oh. S on the car of that guy. Because count occurrences takes 2 parameters, a symbol and an S-list, and this guy also takes a symbol and an S-list. So I just didn't tell it what I was looking for. And there's our 3 for that guy. And let's give it one of the more complicated ones. This guy, well, actually the first one had its search and S-list as well. Oh, I have to fix my... Was it supposed to give me a 3? It was. And then we can test it on our last one. This guy should give us a 0. And there's our 0. All right. So walking through this again, count occurrences takes the thing we're looking for and an S-list each time through. Well, we know we're done when we run out of stuff to look at. That's a pattern, right? We've seen that pattern a bunch of times. So when that's the case, just finish with a 0 because I'm doing some addition as we go along, so I just won't break anything I found. Otherwise, I could be hitting, if we think about, now, kind of from our instruction part of this is, remember we talked about grammars last time, okay? The grammar for an S-list is, it's either a symbol or it's an S-list. It's a list containing a collection of symbols and S-lists, right? Note how this looks like that grammar. This is when I'm done. We're out of stuff to look at. Otherwise, I'm either looking at a symbol or I'm looking at an S-list. That's the grammar, is it not? If it's a symbol, then I'll ask the question, is it the symbol I'm looking for? Does it match the guy I was searching for? If it does, I found one, so I'll add one onto whatever count occurrences returns for the rest of the stuff I haven't looked at yet. Otherwise, if it wasn't equal to that guy, I'll just go ahead and call count occurrences on the rest. If it makes you feel better to see the difference, you can always say +0 count occurrence like that. If that just gives you a visual way of saying, well, I found one, add 1. I didn't find one, add 0. Go ahead.
Is there any functional difference between an S list and a just multi-dimensional list?
Well, S list is something that was defined by the book. It's not a scheme thing.
Right.
Yeah. So when you say a multi-dimensional list, if you put a number in there,
Okay.
numbers aren't allowed in S lists. So there's one thing that breaks it. Yeah, that doesn't mean that's a bad thing. It's just that's not what the language of S lists is.
Okay.
All right, so I'll go ahead and leave it like this. I mean, it'll give you the same result, but that might give you just a little bit of a visual helper saying that if I found the guy that I was looking for, add 1. If I didn't, add 0. Does that feel a little better when you visually see it? It's not necessary to add a 0. It's never necessary to add a 0, but if that gives you a little bit of a structural. So this is really our first piece of our grammar for S list. If it's a symbol and it's a symbol we care about, add 1. If it's not the symbol we care about, add 0. In either case, go ahead and call count occurrences on the rest of this S list. Otherwise, if it wasn't a symbol, I must be looking at an S list. The car of our S list must be an S list itself. What do I do to S lists? I call count occurrences on them. So I'll go ahead and add whatever count occurrences for the first S list, the car of the list is, onto whatever count occurrences happens to return for everything else in my S list. So I'll get 2 numbers out of that. We'll just add those numbers together. We don't know how scary this car S list might be. It might just be a list of A and B, or it might be a list containing an S list, containing an S list, containing an S list, containing an S list, containing a S list, containing A, B, C, followed by an S list. So, make sense? All right, so that's count occurrences. Question on that one. So I'll go ahead and give that to you as a This was 1.19 and 1.20 solutions. Okay. Let's look at what comes next. All right, so let's go ahead and let's look at this very next one and let's solve it together. All right, so it's a 2-star, so that means it should be extra easy. So it's something called product. Okay, product takes in, let's see, SOS1 and SOS2 are each a list of symbols without repetitions. All right, so this is just a list of symbols, not an S list. Just a list containing symbols. Specifically, it's a list containing unique symbols. Make sense? So it would not allow you to have the list A, B, A, because A can't appear twice in it. It says where SOS1 and SOS2 are each a list of symbols without repetitions. This guy should return a list of 2 lists that represent the Cartesian product of SOS1 and SOS2. All right, so the product of A, B, C, X, Y will be AX, AY, BX, BY, CX, CY. Make sense? So we're creating a bunch of 2 lists where each element of the first list is put into a 2 list with each element of the second list. Go ahead.
Do you want us to specifically check that they don't repeat, or do we just have
It tells us that SOS1 and SOS2 will not have repetition in them.
Okay.
Now they could have repetition across the 2 of them. So this could be the list ABC and the list AB, which is fine. So then you'd have an AA, an AB, a BA, a BB, a CA, a CB.
So it's like matrix sort of thing.
Huh?
It's like matrix sort of thing.
Matrixy stuff, yeah, Cartesian products, right. All right, so we're going to call this guy product. We'll go ahead and dump all that crap so it's not in our way. Okay, so define product to take a lambda, SOS1 and SOS2. All right, so I'm going to do something to each element of the first list, right? So let's just make that first pattern. So we're going to say product is going to go through each element of SOS1. So if null SOS1, go ahead and boil down to the empty list. That's a pattern we've seen a bunch of times. I'm going through SOS1, every element of SOS1, until I run out of elements in SOS1. Now, if I still have an element in SOS1, what am I going to do with it? I want to create a to list with it and every element of SOS2. Right? So we can give ourselves a little helper here. Define product helper. And this guy will take in a lambda with a symbol and a list of symbols. And his job will be to create a to list of every single one of those symbols. If null list of symbols, boil down to the empty list, else cons the list containing S and the car of list of symbols onto whatever is returned by product helper of S and the cooter of list of symbols. So this guy is going to produce a list of two lists where each element of LOS will have S, will now be paired with S in a to list. Make sense? So, if I'm not dealing with the null S list, what am I going to do? I'm going to append something. I want to append the list that is returned by product helper, passing it the car of SOS1 and the entire SOS2 list. And I'm going to append that onto whatever's returned by product, passing it the cooter of SOS1 and all of SOS2. Let me steal something here.
Line 14.
Who?
You have a parenthesis starting.
Oh,
No, but you want to 14 in front of SOS2.
oh, thank you. So here's our list containing a bunch of to lists. I think those are the right two lists. That make sense? All right, so this one, had I given this to you as homework, would have probably taken some time, right? Okay, but understand, but I mean, the reason I did this, I mean, we did this in what, like 4 minutes. The reason we did this way is notice that we're seeing the same patterns pop up over and over and over and over again. And really try to pay attention to the way I'm going about it. Think about the words I'm saying out loud. Okay? This isn't just like memorized code, right? We're saying, what do I want to do? For each element in the first list, I want to create 2 lists with each element in the second list. So I created a nice little helper. All this guy does is solve one problem. He says, I will take this symbol and create a list of 2 lists with each guy in here. So this solves a much simpler problem that is a subset of the harder problem, right? So whenever I need to solve this problem, that is, whenever I need to call this helper on the next symbol in SOS1, along with all of SOS2, this guy will do the job for me. And what will he give me? He will give me a list of 2 lists. And then I'll call product on my next element of on the rest of the elements of SOS1. And what will he give me? He will give me a list of 2 lists. And if I want a single list of a bunch of 2 lists, I need to append those guys together. That makes some sense? All right, so for your homework, let's do 2.2 and 2.3. And I'll go ahead and give you 1.21 in Slack. So 1.22, 1.23. Sound good? Questions, comments, concerns, bribes? All right, I will see everybody on, what day is today? I'll see everybody on Wednesday. So this was 1.21.
Can you assign something new? I started
What'd you say?
Did you assign something new?
Yeah. Next 2.
2.3?
2.2, 2.3.
Gotcha.
Do 2.2 and 2.22. No, 1.22.
Yes.
And 1.23 for Wednesday. And I'll get it up on Blackboard, but for when I forget to put it up on Blackboard, this allows you to at least get going.
It's funny how,